Okay, so we're still looking at the end of chapter 5 in torsion, and we're looking at irregular shapes. We'll be looking at thin-walled tubes. And so this is another example of an irregular shape. It's a square cross section, but this time we're looking at an indeterminate system. And you're going to find the approach is just like if it were circular. With an example like this, I like the force method. I'm going to remove a redundant, allow rotation, put my reaction back on. So in some ways, it's a nice review. So we have this aluminum strut. It's fixed between two walls, A and B. It has a 2-inch by 2-inch cross section. So let's just go ahead and draw this out. And I know that it's a 2-inch by 2-inch. And if I go and look at the chart, then these sides are called A. So A is 2 inches. If I look at our chart in the book, and I'm going to find my shear stress, it is 4.81 torque divided by A cubed. So we're going to have, is that correct? Yeah. And then our angle of twist for a square section is 7.10 TL. And then we have 8 to the 4th and G. So instead of using the equations we've been using for circular, we're going to be using these. So I am going to start with equilibrium. And when I look at equilibrium, I have 40 pound-feet, 20 pound-feet, and I'm going to assume that my reactions go backwards because they look like they will. And so when I sum these torques, to the back is positive, I'm going to have reaction A minus 40 minus 20 plus reaction of B equals 0. So reaction A plus reaction B equals 60 pound-feet. And I need to keep up with my units, okay? Normally I'm going to be working with kips and inches when I'm in pound-seconds. So I need to make sure as I'm setting up equations, I'm going to be dealing appropriately with my units. And now what we're going to do is we are going to look at compatibility and deformations. Compatibility. And I'm going to use the force method. So the first thing I'm going to do is I'm going to remove my redundant at B. So my wall is fixed RA, and I have 40 pound-feet coming towards me. I have 20 pound-feet coming towards me. And so if I were to look at this shaft, I can see that it's going to rotate some amount due to the applied torques. Okay, due to the applied torques. Well, as I work my way backwards, this segment from D to B is rotating. It's just going along for the ride. There's nothing internal, the internal torque, as I'm going backwards, because this is my rotation. So maybe I'll make it like, there's my rotation. Okay, as I'm coming backwards, no internal torque. As I hit from D to C, I can see all of a sudden, oh, it is going to have an internal value. Oh, it is going to have an internal value. So how can we determine this rotation due to the torque? It's going to be the torque that's internal from D to B, length of D to B. Actually, it's not, because we don't have a circular section. We actually have this. So I have 7.10 torque of B to D, length of B to D, divided by A to the 4th G, plus the 7.10 torque from D to C, length of D to C, A to the 4th G, plus 7.10, the torque from C to A, the length of C to A, divided by A to the 4th G. So I have to be able to find these internal torques. Well, we already established that if I cut back here, positive torque from B to D, this equals 0, because we don't have anything external. We took that wall away. Now when I make my cut here, go across, I have 20 pound-feet. I'm going to assume positive internal torque of C to D. And when I sum these up, the internal torque from C to D is a positive 20 pound-feet. And now I can go back and cut here, use all of this shaft. Let's put this underneath. Okay, so now when I go back and look at the entire, we have nothing, we have 20, we have 40. As I make that cut, we're going to assume positive internal C to A, and we can see then the torque from C to A is a 60 pound-feet. So we can plug those in, and then we have our links and our material properties. Well, it can't really twist. So now we are going to, okay, we've kind of assumed that it's twisted, and we are going to reapply that torque at B, that resisting force at the wall, okay, to twist back. And as I look down the length of this, it is the same material, it is the same cross section, which is beautiful because now instead of 2 feet, 2 feet, 2 feet segments, I actually have 6 feet of all the same material properties. When I draw my internal torque diagram, I have TB, I assume positive. Okay, so that's going to be the torque from A to B. That's all of my internal. Okay, and that torque of A to B equals negative torque B. Okay, I'm going to sum these up. That's actually coming towards me. So when I'm looking at this rotation, due to the wall actually being there, I get negative TB, negative 7.10 TB L of A to B, A to the third, G. Okay, and what do I know about the rotation? I know that the rotation due to the torque plus the rotation due to putting the wall back has to equal 0. They are starting and stopping at the same points. Okay, so I can set this mess equal to this mess. So let's go ahead and get that set up. And I'm going to note that as I'm adding this up, this 7.10 is the same, a to the fourth and g are the same, so I'm going to pull that out of my whole equation. 7.10, okay, over a to the fourth g, and then I have this internal torque from D to C, which we already determined was 20. So I have 20 pound-feet times length, 2 feet, plus 7.10 a to the fourth g, okay, times internal torque, 60 pound-feet, times 2 feet, okay, plus 7.10 over a to the fourth g times negative TB times 6 feet. All of this equals 0. So I can take these things, multiply to the other side, and magically, poof, they go away. So I have 40 pound-feet plus 120 pound-feet equals, take that over, negative 6 TB. And I'm going to take out the feet. So I have 160 pound-feet divided by 6 feet equals, negative comes over, it's positive, torque at B. It's not just all in pound-feet because it's actually pound-feet, feet squared, pound-feet, feet squared, pound-feet, feet squared. So when we get our units out, it'll be a pound-foot is what we end up getting for our torque. So let's look at that. 160, 60 divided by. So the torque at the wall for B is going to be 26.67, okay, pound-feet. I can go back to my equilibrium equation and TA then. If I look back at TA, change sign 60 plus, I get 33.33 pound-feet. And now, if I wanted to calculate anything here, I can use these torques because I know that this is coming back here, torque A at 33.33 pound-feet. So if I want the angle of twist to C, as I'm coming here, I've got external 33.33. I'm going to assume positive internal. I can see it's positive, but the torque from A to C is also got to be 33.33 pound-feet. And so the angle of twist from A to C is 7.10. Torque from A to C, length of A to C, divided by A to the fourth G. And I can calculate then that angle of twist from A to C. I can also go back and make a torque diagram and find internal shear stresses to make sure that we don't have yielding. But this is the general setup for this type of a problem. And again, it's a problem we've done multiple times.